Hello, welcome and an excellent evening to this Let's Code MS-DOS episode. And we are going to go back to a couple of basics, namely data types in the C programming language, because I think there are some people who still have maybe questions about that. So we are gonna go through all the different types, and I've coded a couple of demo functions. I won't type them down as I usually do because I will be mostly doing explanation and the typing will be probably distracting from that. And the C language is actually very simple when it comes to data types. There are two numerical data type categories. There is not really a string data type, but something that we use as a string. Then there's a special data type called void, and then there are structures and unions. There are also pointer data types, which I will very shortly talk about because we did a video about memory management and pointers previously. So those are types as well, but basically everything that you can have a type of, like integers, floats, and void even, and structures, you can also have pointer types. So basically that's that being said. And we're gonna start up with this function up here about integer data types. And here are all the data types, integer data types that you can have, including some redundancies. The character is actually an integer data type. You can calculate with it, do arithmetic, whatever, but it's usually used to store single characters, basically. If you use the char data type to declare a variable, it will usually be signed, so you can go from -128 to 127, but that actually depends on the compiler, because the standard doesn't say anything about that. So in the options of our compiler, we can go to code generation and we can select the default char type to be signed or unsigned. Most implementations will leave it at signed, but if you really care about what data goes into the char, just say unsigned char or signed char. And of course you can also redefine your own data types, which are not new data types, that must be said, but you can, for example, say typedef unsigned char byte. And now we redefined, or we made an alias for the unsigned char data type to be also called byte. So I could also say byte b equals something. Alright, so this is something special, so to speak. And that goes for all the other data types as well. The type def is not a type definition, it is an alias. There are only the built-in data types plus the structured data types from which you can create as many as you want. After the char data type, which is 1 byte long usually, is the short data type. Short is signed if you don't say anything else. You can also say unsigned short or signed short, or you can even say unsigned short int for the complete name of the type. But all the integer data types except for char are signed if you don't specify the signedness, basically. And on TurboC it is 16-bit wide from 16,385 negative to 16,383 positive. Then you have the regular integer data type, which on TurboC is the same as the short, which we'll shortly see. Haha. And you can also have the unsigned int and signed int variants. Then there is the long integer, which on TurboC is 32 bits, and the unsigned long and signed long. On more modern systems, you will have different sizes. There you might have 16 bits for the short, 32 bits for the int and 64 for the long int, for example. And there might be a long, which could be even longer, but here it's also 32 bits. To see what the size is of a type, we can take the size of operator of either the type, or for fun I put the variable names in here, which is the same because it looks at the underlying type and tells you what the size of it is. And let's run this. Should be working fine. And here you can see a char data type is 1 byte, which is exactly what we expected. The short and the int are the same on Turbo C. It's 2 byte or 16-bit. Long is 4 byte and long is also 4 byte. So those are all the integer data types that you get in Turbo C for MS-DOS. If you use GCC or CLang on modern 64-bit systems, this will vary, obviously. You can try that out. Okay, next up are floating point data types. Those have a certain precision. They can display or represent fractional parts of a number. This would be 1.234 times 10 to the power of 5. Scientific notation. The exponent can of course also be negative for small numbers which are smaller than 1. And yes, you can have either the float, the double, or the long double. And floating point constants in your program will be suffixed by f if it's a regular float, or you will leave it out if it's a double. We can also again take the size off of that to figure out what the size is actually. And let's enable this part of the code. Let's move this down here and run the code again. The output will get a little bit longer. Floating point types, a regular float is 4 byte, so the same as a long, 32 bits in precision. A double will be double the size with 8 bytes or 64 bits in precision. And then on Turbo C for MS-DOS, you also have the long double with 10 bytes or 80 bits of precision. This is exactly 80 bits are exactly the number of bits that the Intel FPUs, so the 8087 and all its successors, use for internal representation of floating point numbers. So if you're using a long double, you will have the same precision in memory as you have on the FPU. Everything else will lose precision if you use that. All right. Next up is string representations. Let's enable that already. Strings are interesting in C in that regard that there's no real data type for them, but they are pointers to chars. So a string in C is just the memory location where a bunch of bytes is, which are just ASCII characters, and at the end there must be a null byte. In your program code you can have a literal, like this here, this is a string, and char star CP will point to this location in memory, and the null byte will be appended by the compiler. And as usual with any pointers in MS-DOS in real mode, you can have far pointers, which not only include the offset from the current data segment, but also the data segment where the string is stored. The size of those pointers is not the length of the string, but really the size of the pointers. So let's try to do that. Let's look at the output, and you can see a regular char pointer, a normal string that is in the current data segment, is 2 bytes, which is 16 bits, which lets you offset into exactly one data segment. And if you need to access strings that are in a different segment, because that's how the 8086 works, you need to declare a far pointer, and that is double the size. So when you are doing MS-DOS game programming or demo programming and you need to be wary of the number of bytes that you use up. Short pointers or near pointers, they are called, are of course more memory efficient than far pointers. But they limit you to 64 kilobytes of data without having to switch the segment register. And that's it that you need to know about strings. And because they are very simple structures, you don't have a separate string class or anything, and all the string functions that you get in the string header will work on char pointers basically. For example, string compare will compare the strings S1 and S2, and it just gets past the pointers. There's no copying of the strings or anything happening. Okay, next up, the void type. The void type you see all the time when, for example, a function doesn't return anything. You declare the return type to be void. So you can't have at the end, you can have a return at the end, but you can't return anything. That would be an error. So you can write return, but there will be nothing here. And also, if the parameter list of a function is empty, you should also write void actually to make clear that there are no parameters to be passed. Otherwise, the compiler might assume, I think even from the standard, that there might be an int parameter or something, I don't know. But it definitely wouldn't tell the compiler anything if there are parameters or not. So usually you should write void in the parameter list if there's an empty parameter list actually. What you can actually have is pointers to void, which are the general pointer. That could be anything. You will see that, for example, in the mem.h. Those functions use void pointers all the time and return void pointers because they don't care what data they are working on. A void pointer is basically working on bytes. Even if a char pointer, for example, on some platform could be more than 1 byte long, in theory, I don't think I've ever seen such a thing, but the void pointer is guaranteed to work on the smallest addressable unit, I guess, and it can be converted into any other pointer. It's basically a placeholder if you want to manipulate the memory directly, like with memset to clear the memory, something like that. And malloc also gives you, I think malloc is in standard lib, gives you a void pointer because it doesn't know or care what the memory is actually pointing to. They are not using a char pointer here because char pointers are used as the strings, so it wouldn't make sense to work on strings in this case, so they gave it a different name, namely the void pointer. And you can, for example, take any old variable, get a reference of that, an address basically with the ampersand operator, and then pass it into a function that takes an int, for example. And that could also first be converted to a void pointer and then converted on the fly back to an int pointer. The size of a void pointer, did we already enable that? No, we didn't. So let's do that. The size of a void pointer is obviously the same as any other pointer. So let's try that again. And you can see a regular void pointer is just 2 bytes as usual, because it's a near pointer. In this memory model at least. But let's talk about memory models a different day, because that's a whole other story that is very particular to the DOS compilers, the real mode DOS compilers. Something more complex. We can also have structures. Structures give you the opportunity to actually model data that is not very simple like an integer or a float. But you might, for example, have a point in a graphics program. You might have a char for the color, and you might have an integer screen coordinate x and y. You can enclose this into a struct called point, and then further down the line, you can, for example, declare a variable called struct point p1, which would be of type struct point. And we could have a different structure for a general point called struct other point that has two double variables, x and y, but no color, for example. So you could initialize those two variables, but you wouldn't be able to assign them to each other. Like here, the other point, we can do something like p2x equals something and p2y equals something, but we wouldn't be able to do p1 equals p2 because the compiler would say those are incompatible types. Illegal struct operation in function struct blah blah blah. That's what TurboC says, because we can't assign different structs, but we could copy structs from the same type. That is actually possible. But you can of course access different elements in there and combine them with elements from a different struct. That is obviously working. You can also take the size of a structure, and that will be at least the size of the sum of its elements. So it will be the size of char plus 2 times the size of an integer. But there might be padding in there. For example, if we force everything to be aligned to word boundaries, 16-bit boundaries, then the size of the structure here would be actually 2 plus 2 plus 2, so 6 instead of 5. We can have a look what this actually is. Let's run this. And we didn't enable this, so I'll delete those comments here and we'll have a quick look. And the size of the struct point is actually 5, but we can go into the compiler options and see that we force word alignment, then rebuild everything by forcing here, and then have a look. And suddenly the size of the struct point is 6. This you have to keep in mind, especially if you're writing structs to disk or read them back from disk. Because then those padding bytes will also be written if you write the struct directly. You need to write serialization functions that write every item as single entities, which is tedious but needs to be done if you have word alignment. Okay, a lot to unpack here, I guess, but one more data type is missing, the union. A union can have multiple items, but those multiple items will be overlaid on top of each other. You can access one thing at a time, and the whole union will be interpreted from its memory contents as if it were that type. For example, we can have, that's the usual application actually. You can find a similar concept in the DOS header. If you look at the int86 function, which calls a software interrupt, there is 2 parameters which are unions, union registers, and these registers have one structure inside, which are the word-sized registers and the byte-sized registers. I've done the same thing here, but I called them the X registers, AX, BX, CX, and DX, which are the general purpose CPU registers that the 8086 has, and the L registers, which are the byte-sized small registers. AL for accumulator low, accumulator high, BL, BH, and so on, up to DL, DH. It is obvious that this should give you a representation either on word level or on byte level. We should switch back to byte alignment, because I'm not sure that this works without that. And we can have a union of those registers, one structure xregs called X and one structure lregs called L. And what we can then do is we can, for example, write to the X sized register AX the value AAFF, and then on reading out we use the L register AL and AH. And we print them out, masking off the unused bits, obviously. And when we do that, we can see that indeed AL contains FF and AH contains AA, which is exactly what we expected. This is the low byte and this is the high byte. If we enable the word alignment, let's see what happens. I'm not actually sure if that works or not. The size of the structure actually grows, but that was the point structure, but this still seems to work, which is nice. That's very nice. We can maybe ask for the size of the union, because that should be useful. The union is called regs, and we do that here as well. And running that gives us the size of 8, which makes sense. 8 is actually 4 times 2, which is the size of these. So here there was not a word alignment, but the union seems to honor still a byte alignment and does no padding, which makes sense. That's very nice. While the other structure gets padded for more efficient access. And with that, you actually are already aware of all the different data types that we have in C. Functions, of course, or function pointers are another data type, but function pointers, maybe we talked about those, but they should also be a topic for a different time. As you can see, the size of the language is pretty small, and the most powerful thing are probably the structs. If you're doing game or demo programming, then you will use the structs quite a lot to model your world, your objects, and everything else. The structs cannot contain any functions apart from function pointers, so you can't easily do object-oriented programming. But that's also nice because that keeps your programs much simpler and usually also quite easy to understand without having to deal with a whole different kind of programming, let's say. Okay, I will put this code up on Codeberg so you can download it and play with it and test it. And of course, share, like, and subscribe. Leave a comment. Did I forget anything? I hope not, but if I did, put it down in the comment box. Also, you can, as always, follow me on Mastodon at chaos.social/@root42. You don't have to get an account there. You can just read my stuff there. But you can also follow me from any other Mastodon server that you like. And I think that should be everything that I wanted to show you today. See you in the next one, and have a very nice evening indeed.